Well, today will come as a welcome difference from the last couple of lectures. Yes, in several ways. One, we're only adding one mechanism. The trick with that is it's a rather open-ended mechanism, which means it can look very different in different places. And it breaks all the rules that we've dealt with so far.
All?
No, but free radical reactions, now we're dealing with single electrons moving at a time instead of pairs of electrons. And so this is going to be like that ROOR hydrobromine reaction where we drew electrons moving towards other electrons because we're using those single barred arrows. So this is all we're going to add today is just basic free radical reactions. But we'll start with a review. One pentyne reacts with each of the following. What do we get?
Yeah. Actually, that was the That's not. Oh, yeah. The normally get a wage, but now we just did. So, the first one.
Yes.
It's on the bottom, we add.
You take away the triple bonds,
We get a double bond.
yes, which then rearranges, right? So one pentyne.
So does it matter what goes on top of it, or what's under the arrow? Stop giving me internet photos. I don't know why myself.
Alright, so this is what we're starting with. We break pi bonds. This is gonna be our hydration, our talking about hydration,
Right, so what? Yeah. All of it.
all of it.
Okay.
So then what we'll get, what we're gonna get is gonna look like that's a bad thing. That was better. We're gonna get this initially. Break 1 5 on, add.
Then we may just, we don't get alcohol, we get it. Garden hills. It's- alright.
So then, sorry, I'm trying to participate in a meeting where they're talking about stuff related to faculty that is scheduled over this class. So I was giving you space, and I was also making my input enough for my fellow faculty.
Is it the double bond shifts over and then?
Yeah. The H moves this way.
Oh, it takes the place. of-
Exactly. So then our final product,
Okay. There. So that's the first.
so that's the first one. Now that we've recapped that, B should be pretty easy.
Two components. Well, we did two, objects. Or like the, I think we did my. Oh, yeah, I have it. We, yeah, for the, initially, we have double bond with the American action. On the more so that's good. Then it reacts again. Wage of yarn, very.
Are you going down?
Yeah.
I was thinking this one was gonna be really easy,
Oh,
because this one is,
it's. So. This, oh, the same. Same thing, but with the OH.
no, the the OH is gonna be there. It's
Oh.
inside our column.
Got it.
So same, and then it'll do the same rearrangement. So your final product for B, go ahead.
BH is what constitutes the amplifier, but the HG on the other one's plus.
Yes.
Okay.
So B then turns into, our first intermediate would look like. Not there, the other side. So still get the enol. It just then immediate, when it rearranges. We get the aldehyde.
Okay.
It's the only difference, just like with alkenes, the only difference, where did you put the aldehyde?
Same start. This is what we did last time,
Uh-huh.
except it's on the.
Inside our cosmic top because the boron.
Yes, okay, that's what I was. There's no way you drew all that. No, it's just the top.
Sorry, since those ones were so tightly linked, I thought we should do that B before we do two little speech better. Now, as you want, continue on.
Take away the triple bond. And all of those single bonds that add three bromine on one. That's, you have to do it from. Okay. Do you want to go down or do you want to go first? Find the on. Yeah. Yes.
Yeah, I don't mind that at all.
That works really well, actually.
I feel like a window washer. Need my squeegee.
That guy who like free solo.
I did see that. That was wild. I can't believe that they let him do that.
I know. He free soloed like a really tall building in a different country.
I think 150 stories or something like
Yeah.
that
Thing.
in Taiwan.
And he just stood on top and was like, cool.
He's a local. Do you know that?
Here?
Yeah, he climbs at Blue Granite. It's the guy who made that documentary Free Solo.
Here.
Is he missing a finger?
Like, yeah.
Maybe Carl's met him at Blue Granite before.
Yeah. I didn't know it.
Yeah.
That is really cool. We should actually do the. So it's. Well, HCl. I was gonna take an educated guess and say that it's basically gonna be the same thing as the last one, but just with HCl.
Maybe just once.
Right. Like the first step, like our initial one.
Yes, we did.
Not with HCl. Well, but chlorine and bromine.
We use them pretty interchangeably. We're going to talk about the differences actually today because chlorine versus bromine makes a difference when it comes to free radical reactions. But for the most part, they're kind of interchangeable. All that's going to change is the rate.
But you still get rid of both.
Sorry, no, I missed one.
Okay. Well, that is not quite weird. Oh, same thing. Same thing. Two equivalents of bromine and BI2. Same as what I bought in CCL,
CCl4, it's just a solid carbon tetrachloride.
which goes on the bottom.
One of the reasons, again, when we talk about free radical reactions, we'll talk about one of the reasons why it has to be in CCl or else it'll react with solvents. So you have to react it in an organic solvent that doesn't have any hydrogens. The carbon tetrachloride is one of the few options.
So it's gonna happen twice, but it's PR2. More.
So with alkynes, when you're not sure, think about what it would be if it was one equivalent with alkene.
Right.
If it was this, we know what that does.
Then it's. Oh,
There you go.
so one goes on back to both sides.
Yeah. So it's not. This is in the neither Marvin nor anti-Marvin category because you're adding the same thing to both sides. Remember that?
So we get two of each side since it's two equivalent.
You do it twice.
We can do it again. As we are. But then when we hit. Are you driving? Yeah, just like. I'm honestly surprised with how much there is. I don't.
Organic chemistry really is like learning a foreign language. The more you immerse yourself in it, the more you get the vocab, the more you'll retain about like the actual sentences in your Spanish class, right?
Right. Almost done. Eight. Last. That was right. Yeah, oh. And street followed by highway. I feel like everyone. Do you write what is in on the bottom of the arrow? I think it goes on top and followed by the bottom. I remember to make. Oh wait, true. That's. Oh. The bar like moves in place of this. It is.
So start by making this first step is just deprotonate the terminal alkyne,
Right.
which now it's a nucleophile and we let it react with methyl iodide.
So that just like an equal thing.
Exactly. So you can still draw it the same. This is definitely one of the ways that's helpful to make sure you don't lose a carbon, is draw it identically in the same orientation and everything, and then add whatever change.
But is it still triple?
It is still a triple bond. Because it wasn't the pi electrons that actually acted as nucleophile, it was the negative charge that nucleophile. I'll give you not a minute, a couple seconds for G, so it's an easy one.
And there's giving two H2.
But even if you don't, you still get 50% yield of the same product that you would have gotten, right?
You told me that.
But yes, we could assume.
Also, they want this. I draw a hydrogen for this one just to go over them.
Yeah, that's totally fine.
H.
All right. How are we feeling? Not so bad, yeah?
Yeah. Definitely better than I thought.
It really is just subtle changes to the reactions we already learned. So in a way, it's helping you study for the alkenes too. All right, let's talk about radical reactants. So these show up most frequently when we have something where we have that has a weak homolytic bond, which usually means you've got the same thing on both sides. And what it does is if you got the same thing on both sides and it's not a particularly strong bond, it means if we control the conditions, we instead of getting to go through a heterolytic bond cleavage where both pairs of electrons go together, we get a homolytic bond cleavage where each of the groups takes one electron of the bond.
You said homolytic bond means that it's the same.
Homolytic means it's the same in both directions. So if we think of
Homolytic.
this is homolytic bond cleavage, so we're breaking the bond in a homolytic way.
Is definite for
Yes.
which one?
So the same in both directions is homolytic. Homo means the same. Lytic means splitting. The analogy for it would be if two people have twins and get divorced, somebody gets primary custody versus the parent child.
Okay.
Usually, this is more common,
Right.
but in rare instances involving Lindsay Lohan, this is more prevalent. I grew up with the really old one from the 60s.
That's what my parents said. They're like, did you watch the old one? And I was like, I think so. And they're like, no, you didn't.
It's probably for the best. It's one of those, mid-century Disney. This probably didn't age well. I don't remember anything specifically, but it can't be good.
I'll see if I can. It's not Disney. I love it. It's not age well.
All right. So what do these look like when we get these free radicals? Because this bond is not going to hybridize the same way as a lone pair. So a lone pair usually makes a hybridization still sp3. Radicals, because it's not a complete valence, it still presents as sp2. So it still presents as trigonal planar, like a carbocation. We're going to see there's a lot of similarities between carbon radicals and carbocations. Including how stable they are. It gets easier and easier to pull a hydrogen off the more substituted the carbon is. So literally the same rules for stability as carbocations. A tertiary carbon radical is going to be more stable than secondary, which is more stable than primary, which is more stable than that.
But you said it's easier to pull the right channel.
Basically, so
It's
what starts these reactions is usually when X and Y are the same thing in this previous slide. If these are the same thing, then we can usually get this to split just by shining light. If they're not the same thing, though, in order to force it to be a heterolytic bond, a homolytic bond cleavage, we need to have basically a little bit more force to do it. So we talk about how easy it is to pull that hydrogen off, because it's not easy. Carbon hydrogen bonds, for the most part, are very stable. So in order to do this and to be left with radicals is kind of tricky. So we talked about the decreasing bond dissociation, which is exactly what it sounds like. Bond dissociation energy means how much energy does it take to just straight up rip them apart. And you can see just based on these numbers, it gets progressively easier to take off the hydrogen the more substituted it is.
One association is how easy it is to pull off.
Opposite. The lower the bond dissociation energy, the easier it is. So it's kind of like you can think of it like pulling magnets off of a refrigerator. The stronger the magnet, the harder it is to pull it off. The larger the dissociation energy, the harder it is to pull it off. So let's practice with that. This is how we draw radicals, because radical is not a charge. It's an incomplete valence. So the atom is still neutral. So we need a new way of writing it. It's not just putting a positive and negative, so we just use a dot to symbolize a single electron.
Middle one is gonna be the most stage, right?
Yep.
So one. And then the right one is gonna be next. And then left to be least.
Good. Easy enough.
Yeah.
Same thing over here.
And we'll just left this.
Yep. So nothing we haven't talked about before. It's just now in the context of radicals, it means it looks a little bit different. What we will see though is a slight difference. Is that resonance matters even more. Before with carbocations, resonance basically put it into that middle category. Not as good as tertiary, but better than primary or secondary. Resonance is even more important with radicals. So the easiest place to pull a hydrogen off is going to be wherever it has resonance. That's the most important factor. And then after that, we look at, okay, if I have multiple places that could have resonance, I'm going to pick the one that's more substituted. And so let's start by just drawing what the resonance structure would look like here, especially considering our arrows have to look a little different now too. Half an arrow. So we have something like this. The two half arrows can go towards each other because that's going to turn into a new bond. Right, because a bond is two electrons. We don't see that with charges because charges are already a pair of electrons. But net result is it looks a lot like moving a charge around the resonance. It's just the way you draw the arrows is a little different. It still is going to sort of alternate carbons.
I mean, neither of those be more stable than the other.
Not in this case, no. So if we had something like this, and we're trying to decide which hydrogen is going to be easier to pull off, there's a hydrogen here that has resonance, or there's a hydrogen here that has resonance. That one's going to be preferential because not only do you have the resonance, it's also tertiary. So if you take our decreasing bond association energy from before, let me adjust the position so we can read it a little bit better. So this is the same ones we had before.
Yeah.
Metal, primary, secondary, tertiary. Primary with resonance is more stable than tertiary without resonance. So instead of just putting everything with resonance goes into the same bill category as secondary, allylic and benzylic is even lower in energy than tertiary. So it matters even more. And the more resonance, the better. The reason that a benzene is 356 is because it's got 3 resonance structures inside the ring, right? Versus only having 1 resonance structure. And we start to see that make a bigger and bigger difference.
Seriously, the more stable it be without that hydrogen, the more
Yeah,
it is.
exactly. Exactly, because for all of these, we're going uphill in energy, right?
Yeah.
So which one is the least uphill in energy is basically, this is tertiary, secondary, primary. It's gonna be a lot easier to get over that bump, which is gonna speed up reactions and in terms of favoring equilibrium. That usually makes a big difference. The only difference really with carbocations radicals is that the resonance matters so much. All right, so with that in mind, here's another practice molecule. Which is the weakest carbon hydrogen bond? Which one's the easiest to pull off?
The one by the forks on going from left to right, 3, left to right. Yeah, I agree.
There is no carbon hydrogen bond there though.
Oh.
That carbon is quaternary.
So then 1.
Carbon 1,
No, it's good. I would say carbon 2 on the other side.
3, carbon 3. You think that one? So that would actually, we can't have any resonance. If we did that, there is no resonance structure for that one because that carbon already has the pi bond. We need one adjacent to that. So that one's gonna be our most stable. Sorry, most stable intermediate, which means easiest hydrogen.
So then that lies because that's a secondary, not a tertiary.
But it's a secondary with resonance, which is its own category now. For free radicals in particular, adjacent to a pi bond, which we call allylic, adjacent to a pi bond is even easier to break apart than a tertiary. By kind of a lot. Right, so the one that you pointed out first, Riley, this hydrogen,
Yeah.
that's not allylic. That's the nilic.
Okay. So like with a double bond.
Yeah. This is sort of a roundabout way of remembering that term, but the reason that we use the word vinyl so often is because we use a lot of polymers made from this molecule, which is called vinyl chloride. When you let it react with itself to make a big long chain where you alternate Cl, 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 etc. That's called polyvinyl chloride, better known as PVC. And basically PVC in different formulations is what makes up everything we call vinyl. Basically, we call it vinyl, like vinyl flooring. Records are made out of the same compound. It's just if you change the formulation a little bit, it's also really good for pipes. So vinyl means attached to the alkene. Allylic means one away. All right. So we're gonna have to add some new mechanism steps because free radical reactions don't behave the same way. All of our mechanism steps from before move pairs of electrons at the same time. So this is a whole nother class of mechanisms. Free radical mechanisms are always going to look a little bit different. Luckily, we've already talked about some of these terms before. Homolytic cleavage. We're going to see that we can basically take a free radical and add it to a ion. We can take a free radical and we can steal a hydrogen from something else. Call that hydrogen abstraction. You can have a free radical take a halogen from something else. And then we can also have elimination reactions. If we have a good leaving group adjacent to a free radical, so it's going to be basically any free radical reacting with Br2 or Cl2. You basically pull that one of those halogens off. You either pull a bromine off or you pull a chlorine off, and that leaves you with another free radical. Right, so we're going to talk about these in more depth after we're going to kind of like classify them here in a second.
Hydrogen extraction, you take the radical and steal hydrogen from something else.
Correct.
What did you take this next one?
It's when you take a free radical and you steal a halogen from something. So chlorine or bromine. No, I stopped waiting for you. So coupling is just when if you have two free radicals that bump into each other, it basically undoes the homolytic. Homolytic cleavage when you started with the bond and you turned it to two free radicals. Coupling is when you start with two free radicals and they form a new bond.
Doesn't go on the same set of point or it undoes?
It's the opposite of it. It can undo it. We don't usually draw it that way though, because then the net reaction is nothing happens. So out of these 5 choices, what type of mechanism step is this showing?
The, which is abstraction.
Yeah. And so if we start with a free radical on a carbon, if it happens to bump into a stable molecule, one of the things about free radicals is they're like that person that delights in ruining other people's good moods. Free radicals are not happy. So when they bump into a happy molecule, they make that happy molecule unhappy. And the free radical goes away feeling better about themselves, but now we have another free radical.
Yeah, it's a bully.
It's a bully. It creates more bullies. And we get this endless chain of bully creation.
Lame.
Lame. This is why free radicals are so bad for your body. It's because basically if you eat something that has free radicals in it, it basically bumps around into your cells, going through these processes where it just creates another free radical. One of them gets more stable, but it makes another unstable one. Well, yeah, especially if one of those things that bumps into is your DNA, you get genetic mutations happening sometimes. So it is one of the main causes of, no, I think I can say the most prevalent cause of cancer in human history is free radicals. It's these steps. Because the number 1 free radical, number 1 carcinogen in the world of all time is oxygen.
I need you to elaborate.
So when you breathe oxygen, you're starting from O2, right? That looks like that. It goes through an intermediate as part of the electron transport chain where you wind up making a molecule that looks like this. I want to say it's a copper over here, maybe. But you get a peroxide bond in the middle of the process. Sometimes this peroxide bond will break free and just start floating around in your cells. Well, if that happens, peroxides generate free radicals if you just expose them to heat or light. So basically, when you make these peroxides as part of the normal electron transport chain, you're also generating small amounts of free radicals floating around in your blood. So, no, there's a silver lining.
Okay.
If the number 1 carcinogen in the world is oxygen and you can't get around breathing oxygen, then maybe don't panic so much about carcinogens and other things, because odds are it's actually the oxygen that's going to kill you. So as long as it's moderate, it's not a big chronic exposure thing, panicking about being exposed to carcinogens is not really that big of a deal, because nothing compares to that one.
Okay.
That's it. Don't take up, smoking cigarettes or anything just because I said that.
Right.
But I don't worry too much about microwaving leftovers in plastic anymore.
Yeah.
All right, so this step is a halogen abstraction. So it's one of these. We start with an unhappy molecule, it bumps into a happy molecule, and it passes its misery along. All right. Yeah, this is one. So there's a couple categories here. If you start looking at things like the number of arrows, the first one and the last one had 2 arrows.
Yeah.
All these ones in the middle have 3 arrows. That's a hint that maybe we can broadly classify things together. The other way to classify these is to look at how many bonds you have before and afterwards, or how many free radicals you have before and after. Because in homolytic cleavage, you start with the bond and you end with two free radicals. Coupling, you start with two free radicals and you end with the bond. For these ones right in the middle, you start with the free radical and a bond, and you end with a free radical, a different free radical, and a different bond. So all four of these have the same net result. And so the way we categorize these is a homolytic cleavage, we call that initiation because it starts the process of making holes.
Okay.
These steps are propagation because you end with the same number of bullies you started with. You made somebody more stable, but you made somebody else less stable. And then coupling is also called termination because we end with fewer free radicals than we started with. For the most part, when you draw a mechanism for a free radical reaction, you have to have all three steps, all three types of steps. Because you can't have a free radical reaction if you don't have something to start it off. And then at the end, when you start running out of things to react, they're going to increase your probability that you get two free radicals reacting with each other. So they're always going to start with an initiation, they're always going to end with a termination, and then the middle section is going to be one or more of these. Usually more, usually it's two propagation steps. So we'll do practice with that in a second. Let's start talking about what these reactions actually look like first, and then we'll take a quick break. So the most common things we see for these free radical reactions are either peroxides or halogens, because they both only have a single bond holding them together, and the two atoms are particularly electronegative, so that tends to make the single bonds pretty easy to break apart. You can shine light on any carbon-carbon bond. If it's the right frequency of light, you can still get the two carbons to split apart and do a homolytic cleavage, but it's way out of the visible spectrum, way past the.
You meant it like that year or two ago. So
Mentioned it.
It's not it's different Latin, Greek, something.
Because remember, for photons, energy of a photon is equal to that h, which is Planck's constant, times mu, which is frequency. Right, so this is basically our shorthand to say we're putting energy in, but it's not the same as doing a delta, because that just means heat. So if you specifically need light, we write it as H now.
It's putting energy or light.
It's putting energy in the form of light. Light is it. You studying waves yet in
This next one.
next quarter?
But what is so new is frequency?
Mu is frequency.
Is that only light frequency, or could you also break them up with like sound frequency?
It's been a long time since I took physics. In physics, you use F for frequency unless it's light, and then you use nu, right? You remember that? Okay, so ask Bruce.
Okay.
Because I only deal with waves in the form of light in chemistry. We don't deal with waves any other way.
Okay.
So as far as I'm concerned, it just means frequency, but I do think specifically it's frequency of light. But I don't remember for sure.
Okay.
What is lambda
That's what that's.
do? Yeah,
You know, the big next to me on the above. No, that's H, that H for the.
that's H.
Okay.
H is Planck's constant.
I don't know.
Planck's constant.
Lambda.
No. Well, actually, you had it back in Gen Chem, back when we did that light lab. Wavelength.
Why did we need this?
Because I'm just doing a little bit of review. Because we use light a fair bit. Also because we're just about to take a break and this sets up a good dad joke.
Okay.
If you ask a physicist what's new, they'll tell you C over lambda.
So bad.
Friend of mine, first time I heard that, a friend of mine came up with that. I'm sure he wasn't the first one to come up with that one, but it is a way to remember this equation.
Yeah.
All right, let's take a break. Let's come back at 11. And we'll start actually looking at, I got distracted explaining HM. The main reaction, first reaction we see with this is a way to pull a hydrogen off of anything organic and put a chlorine or a bromine.
Okay.
So we don't have any reactions with alkanes yet. Basically, the only reaction that an alkane can do up to this point was we could burn it and make CO2 and water, right? This is the second reaction that an alkane can do. Is if you put a halogen, specifically it's got to be bromine or chlorine. Because chlorine is too reactive and iodine is not reactive enough. But with these two, if you shine light on them in the presence of something with a carbon, it'll pull a hydrogen off and replace it with chlorine or replace it with the bromine. So this is how we make all of those halogens, those alkyl halides that we use for all of our elimination and substitution reactions. We make them with this reaction.
Or we can do that.
I believe I have I'm not sure if it's next week or right after the midterm. But we do have a bromination lab. Because chlorine reacts faster, but it also reacts faster. And then you have to have chlorine gas present. Bromine's liquid, you keep that in the solver.
Right.
All right. So that's the setup for everything else for today. Sure. This is definitely one where we want to see it as many times as possible. This is the only mechanism we're adding today. For this reaction to work, it has to start by doing an initiation step. So the initiation step that you break apart what?
Well, the carbons go their separate ways, then we each take the check.
We parent trap it, but is it the carbon that does that?
It's the bond.
So halogen. So initiation is always going to be one of the either the halogen or the peroxide leaving to make it. So if we have this and we shine light on it.
So the halogen or the peroxide causes.
The halogen or the peroxide, the light causes the divorce. Because here's our divorce right here.
The light is the mistress.
The light gets in there and stirs things up.
So the halogen or peroxide take children.
Correct. So then you get a chlorine radical on one side and an identical chlorine radical on the other side. And we know it's initiation because we ended with more free radicals than we started with. So then the question is, okay, what happens after that? Propagation. Which is where one of our bullies runs into something stable and makes it different, right? And makes it unhappy. So It's always going to start with whatever free radical you made in step one is your first reactant in the propagation step. And then whatever you're sticking the halogen on is your other reactant. So if we have a methane around, we get a hydrogen abstraction. So what does that leave us with? The chlorine radical pulled the hydrogen off. So we made a new bond between hydrogen and chlorine. So what does that look like?
Chlorine attached to the carbon.
Not yet. Chlorine just grabbed the electrons here. It just grabbed the hydrogen, for starters. And that leaves behind a carbon radical.
Okay.
So then the next step, all we did was we took the bully that we started with, we made a new bully. Second propagation step, you use the free radical you made in the first propagation step as one of your reactants. And here's the other trick with these. Your propagation steps, when you add them up and you cancel out everything on both sides, should add up to your overall net reaction. So in other words, we don't want any free radicals when we add these. Any free radicals that we make or that are part of a propagation step need to cancel out. So we made a methyl free radical, so we're going to use it as reactants. We started with a chlorine radical, we need to cancel out that chlorine radical. So what could this react with that will give us our final product and also a chlorine?
Also, if we do it, no skill. Yeah.
Cl2, maybe?
This is be two.
No, but watch what's going to happen. Well, the whole point is that we want these to add up to our overall net reaction.
Okay.
Exactly.
We won't use one of them, so we need to use the other one.
That's for termination. We're gonna do that. It's gonna be this, we're gonna do another one of these.
Well,
We're not worried about this balancing with the initiation step. We're worried about the propagation steps need to add.
but okay. Probably not expensive balance. It's process.
And so what happens if we add our two propagation steps together?
Now we can put the parameters together with the stage.
Well, if we just added these two together, these are happening simultaneously. If we want the overall net reaction, you can just add them together. And anything that shows up on both sides cancels out. Remember Hess's law from Gen Chem where you talk about adding reactions and adding their energies, right? Anything that showed up as both a reactant and a product, when you did that, disappeared, right? Not quite, it's still propagation because each of these steps left with the same number of radicals we started with. This is just checking is there another propagation step in there? But if we add these together, we've got a chlorine radical cancels chlorine radical. Methyl radical cancels a methyl radical. Methane and a Cl2 reacting to make HCl and chloromethane, which is what our balance reaction.
Wait, so who cancels what?
Yeah, I'll say that again. So when the two propagation steps we have, we used a chlorine radical and then we made a chlorine radical. So they cancel out. Yeah. All the stuff that's unstable tends to be both a reactant and a product. It's intermediate. It gets made and then used up.
Okay, so the steel from the first three propagation takes out the one it made in the second propagation. Yeah. And then this. And then here's going to be the. Okay, go again. When you said the CO2 and the methane reacts to make HCl and so that it cancels because it's in what we're given.
We want when we write our propagation steps, if we do it right, when we add them together, we get this, our overall net reaction. So our overall net reaction is CO2 plus methane gives us methyl chloride, chloromethane, plus HCl.
So B of the H is the C from the CH4 and then make the CH3 in the down bottom. And then one CL. No, it's.
So chlorine radical
Yes.
steals a hydrogen
Well, what
and makes this.
who eliminates two?
Anything that's identical on both sides. When we add these together, if we add these all together, we're going to get four things on each side, right? We're going to get chlorine radical plus CH4 plus methyl radical plus Cl2. All of that reacting to make HCl plus methyl radical plus chloromethane plus chlorine radical. With me so far? We wrote it as two separate steps here because they happen sequentially, one then the other. But the overall net reaction of both of those is, okay, well, if we want both of these to happen, we can add them up and our net reaction is going to be all of our reactants plus all of our products, or gives us all of our products. Anything that's both a reactant and a product, though, cancels out of our net reaction. This is our total reaction. This is everything. We want to cancel it out to just get the net. So we can say, okay, well, HCl doesn't cancel out, but methyl radical does. Chloromethane doesn't cancel out, but chlorine radical does. And then what's left after we do that?
Exactly what we already given to us.
Exactly. So that's what I mean by the propagation steps should add up to our net reaction. Once you've gotten that far, termination's easy.
I got an A teaching.
For termination, you just take whatever radicals you canceled out up in propagation and you let them react together as radicals.
From the same side or opposite side?
Well, either because they're both they cancel out, right?
Right.
So we have chlorine radical here, chlorine radical there, and methyl radical here, methyl radical there. So basically, methyl radical and chlorine radical are what cancel out, right? So the termination step, we're just going to show them running into each other.
Okay.
So CH3 radical plus chlorine radical. When those react,
And termination is just the canceled ones reacting.
yeah, which is going to give us one of our products we have over here. In this case, it's going to give us methyl chloride. Well, I was going to take break 15 minutes ago, but you asked just the right question to lead into what we're going to do immediately after break. So this is how you do a mechanism for a free radical reaction. Initiation, propagation, termination. The trickiest part is usually making sure your propagation adds up with the net.
It's like the levels of the whole, we initiated, and then there's a whole bunch of propaganda. And then eventually we get into your settings different entities.
That's the dream when it comes to programming somebody for the goal. But
Yeah. And it starts with divorce.
yes, we've got a lot of mixed social going on in this one. But now that we're used to thinking about this as split custody, it's not a bad analogy. It just keeps going. You've got your single parent. It acts as a home wrecker.
Right.
And now you've got a new blended family, but another home wrecker on the loose.
Yeah.
All right, let's take our break. Let's come back at 20 after, and we're just going to talk about specifics of which hydrogen you would pull off. I'm going to look at that during our break, and we'll see what we're looking at, because I do need to make sure I get through the problems that are on the quiz this week.
Yes.
I actually through Windows, I went over to check the other complex projects from, or labs from one Tuesday, I've never had them.
Why not just get the whole bouquet of
Right.
formaldehyde and ether?
Makes me feel like in real organic chemistry. Yeah.
Hey.
I figured out the problem.
Thank you.
I did.
I good.
You have to. This is true. I did it all on my own.
Nice. Okay, so how do you deal with the fact that they're both in your class?
They mellow each other out.
Really?
Yeah.
It's an interesting sister dynamic.
Sometimes best mistakes. You just wait and see how.
Well, they're second year students. They're supposed to be self-sufficient lab. I don't think you don't need my help to set up a distillation again.
Please. So do you have like a single name for them? Have you combined them yet?
No, I make them they don't get to work together in labs. They have to do separate.
No, I just mean
but
like,
just in
you
general.
don't even address them.
The
Is
undercover,
it, is it like
the science sisters.
sisters?
The Valence is taken to them, so Valence just calls them Riley and Taylor. So
I've only called you Taylor one time,
Yes.
but it was of course when Kathy was
Yeah.
popped in.
mhm.
But like I was like, I know it's gonna happen, and I gave her permission to slap me.
Okay.
So
I responded and they're like, spot. Sorry, I'm used to it.
so I'm the only. So I answer to our staff, right, all of them.
Yeah.
If I know, like, it's.
Yeah.
Right. And that's what she would say, that's this out, she ran away. So that by the time they got to hers.
She was nowhere to
she
find. Smart.
Oh, yeah.
That's good. Littlest sibling.
Yeah, that's thing.
Yeah.
Youngest stuff. Yours is gonna be a thing.
It's gonna be interesting. He is feisty, and he's
smart
used to
as a
get.
whip and-
And he's used to getting his way because if he can't get it out of me and Laura, then he starts going to his siblings who are now old enough to help him find things. So,
He's gonna be trouble,
yeah,
but the good kind of trouble.
right. I mean, yeah, we're talking about the trouble they get into is Valence makes them both chocolate milk in the mornings on the weekends. It's terrible.
Rascal. All right.
I should explain like question. Oh, we did.
Oh,
That.
oh yes. Sorry, frequency. Use F or just new. Is new specifically frequency of light? Or is
See a sound.
Okay, so I never used. So I don't know what you're talking about.
But we're.
No, yeah.
you don't write it that way?
No, HF.
Oh, yeah, we don't use that for any frequency. We only deal with frequency of light. So the question was, is it just frequency of light or is it frequency period?
I don't know, because I'll say.
Because you wouldn't use it.
Yeah, so like this same one that's equals HF.
It's interesting where we don't overlap because we never use rho for density in chemistry. It's always D.
We always use right.
We always. She actually, her background is biophysics, right? I think, so she comes more from the biochem world to physics that way, so.
My background is within optics and there's that is, so whether you're talking about the frequency of a physical wave on the ocean, frequency of a light wave,
It's all the same.
just, I've
Yeah.
always used
So this is the chemist shorthand for light.
it.
So, and
Because to me, because when I see E equals HF, that doesn't necessarily just.
Okay.
Because that's
energy.
true of all waves.
but H is not the same for everything.
No, H is Planck's constant.
Really? It's just the frequency is so much lower for everything else. And
So
yeah, okay.
It's what we call the de Broglie waves. So
Oh, right.
it's like matter is wave as well, but your de Broglie wavelength is so tiny.
Yeah,
It's the other way, or no, your de Broglie wavelength is so large that you don't even break.
right.
So then your frequency is so small, so the energy jumps.
Yeah. Okay. That makes sense then.
Anyway.
No, that's all relevant. That's we literally were.
So users, it probably depends on businesses to talk to and the background of services.
Because you don't get to use the dad joke thing. What's new? See Overlanda.
No, I don't get to use that one.
Your loss.
I mean, that is true, that's a pretty good bet.
It's pretty good.
See, now,
I love giving him homework.
Well, you-
All right, see you, Bruce. All right, let's. The very next slide is literally what we just did on. Or break. No, it's perfect. Because now we get to say it again. First step is initiation. Then we do propagation, and usually propagation is 2 steps. There are cases where propagation can be more, but they always have the same result. Propagation should add up to give the net reaction. So chlorine radical, chlorine radical, methyl radical, methyl radical, we get methane, chlorine, chloromethane, and HCl. And then when it comes to termination steps, you can, technically, it's a termination step if you take any 2 radicals and have them react together. So you could just undo the initiation step, but that's not the most common way to do it. The most common way to write the termination step is to write the 2 radicals react the way that gives you your net product. So this is the one that we drew before class. Technically, you could have said 2 chlorines run back into each other again, and turn back into chlorine gas. Or you could have said 2 methyl radicals run into each other to give you ethane. That's also true. But that's going to be a lot less likely because the odds that either of these lasts long enough to bump into another one is pretty small. They're going to bump into something else first. No, you pick the one that gives you the net product. So because this is the one that gives us chloromethane, that's the step we draw. All right, if we do this more than once, if we have a whole bunch of chlorine, we can go until we run out of chlorine.
So this is kind of like the one where it all, you know, all this natural.
Not. I wouldn't say that.
Okay.
Because this just means that it's more like the HDR. We had 2 equivalents of HDR, so we did HDR reaction once and again. Every carbon hydrogen bond can be pulled off by a halogen reactor. So if you have enough of your halogen, you go until you run out of H's. But it does go sequentially. The first thing you get is on average 1 chlorine. And then if you do it again, you get dichloromethane. You do it again, you get chloroform. If you do it again, you get carbon tetrachloride.
But I thought we only went until we got like the initial.
These would be, we think these would be separate reactions. If you do methane plus 1 chlorine, you get this. Methane plus 2 chlorines, you get this.
Okay.
And these are this is definitely, these 3 radical reactions are so unstable, those intermediates, that really you get a mess of products because it's all just based on random things, right? Whatever that chlorine radical runs into first is what it pulls hydrogen. So just for this first step, the major product is going to be the methyl chloride, but it's going to have a little bit of dimethyl or dichloromethane. Because if it happens that a chlorine radical runs into a product, it does it again. So you kind of get, these are very messy reactions. The first polymers that got made in the 50s, basically, the first plastics that were made for public use were all these, and they were all just messy stuff. Because not only these free radical reactions are just really random, which is why they don't dissolve. Like modern plastics dissolve in acetone pretty relatively easily. You take a piece of Tupperware from the sixties and you put acetone in it, it's not going anywhere. Mostly because it's just this huge network of intertwined, bonded chains. I mean, the stuff that they made was so stable. It's like using vintage Pyrex. Like, yeah, it's way better than the stuff we have now. I mean, even to this day, stuff from the sixties is still like flexible and holds shape really well, doesn't melt easily. Even when it does melt, it doesn't like fall apart completely.
Yep.
Yeah, old plastic is not sustainable, but the stuff that's still around is really good.
Yeah.
But we've switched away from that in the name of being cheap and sustainable.
I mean, we use glass.
Yeah, glass is better, but the old plastic is still pretty good. All right. Let's look at this reaction and think about the thermodynamics here. Do we get a big difference in entropy from one side to the other? Remember, with addition and elimination reactions, entropy played a big deal in which side was favored by equilibrium, right? Is that going to be true here?
I think they're the same.
Yeah, roughly the same. If anything, you could say that this is a little bit more entropy because you don't have two atoms bonded that are identical bonded to each other, so it's a little bit more random. But it doesn't dramatically favor either side. Start with two molecules, we end with two molecules. So then what about enthalpy? If we look at bonds broken and bonds formed, are we breaking stable bonds or are we making stable bonds? Both is better than neither, right? But is a chlorine-chlorine bond a particularly stable bond? Carbon chlorine, though, is relatively stable, and hydrogen chlorine is relatively stable. We're making things that are more stable. So that means that our products are favored by enthalpy. Also means it's exothermic.
So it gets hot, right?
It gets hot. The surroundings heat up because the bond energies went down. So because the bond energies go down, it has to go to the surroundings. All right, so if we look at these delta H reactions, turns out fluorine gas is stupidly exothermic. It's like almost as exothermic as a combustion reaction. Like you could make almost as much heat with this reaction as you can burning methane.
Okay.
So generally speaking, we don't want that. It's too exothermic. It's going to react too quickly and be dangerous. Fluorine. And fluorine gas in general is perfect because it's super toxic and super reactive and it's very small, so it's hard to keep in canisters as well. Turns out these gases will actually migrate through the pores in the metal in these canisters if they're small enough. That's one of the big problems with hydrogen cars. Is that hydrogen's the smallest gas you can have, and so physically containing hydrogen in a cylinder requires really, really thick walls. Fluorine has a little bit of that issue because it's so much smaller than most other gases.
So fluorine reacts too much, it's too exothermic, so it's really.
Correct. So no point. Chlorine's exothermic, but less so. Bromine is exothermic, but even less so than chlorine. Then iodine actually goes uphill in energy to make the product. So basically, iodine can't be used for this process.
Because it's too exothermic.
It's
too
endothermic. You're actually going uphill in energy to do this. So shining the light on the iodine doesn't necessarily give you the product because if two iodines run back into each other, they'll just make more iodine. That's actually more stable where you start. So we only are really gonna see this with chlorine and bromine. Chlorine's harder to work with, but it's faster. Bromine's easier to work with, but it's significantly slower. Turns out that can actually be a good thing though, because that actually means that bromine is a lot more selective about where it reacts. And so either of these is going to give us the same net results. If you shine light on, they break up, but then the intermediate step is where we see a difference between these. Because the intermediate step for chlorine is still downhill in energy. If it's still downhill in energy, that means it's gonna react really quickly. Versus if you look at bromine, bromine's uphill in energy to get to that intermediate. Bromine radical is more stable on its own than it is to make a carbon radical. So then we have intermediates, we have net reactions. They're both downhill for their net reaction. The overall energy is still downhill, but the difference is that for chlorine, intermediate is downhill.
The chlorine, like, it's easier, like, to work with.
It's faster to react. Because chlorine is gonna look like this. There's your initiation step, that's really fast.
Yeah.
Because you're going downhill in energy, it's much slower. Versus with bromine, you have to go uphill in energy to get to that.
What?
A lot of uphill. So that difference in the size of the activation energy turns into how fast the reaction is, but also into how selective it is. Because this whole thing is going downhill super quickly, chlorine reacts with whatever it bumps into first. Bromine takes its time and selects the best possible hydrogen. Since we're talking about going downhill in energy, we can use a skiing analogy here. Chlorine is that person when they get on the slopes, they just start bombing down and they're just doing as many laps as possible. Bromine is that person who stops, looks at the map, figures out what the best route is, so that they get fewer laps, but they are better laps. Right, so bromine's slow, steady, chlorine is just cranking through. Right, so let's talk about selectivity. This is the last big piece that we need before the quiz. If we just said that all of our hydrogens were equal in terms of how easy they were to abstract, how easy it is to pull them off, then we would expect if we're going to chlorinate this molecule, well, there's 6 hydrogens that give us the 1 chloropropane, and only 2 hydrogens that give us 2 chloropropane, right? So basically the statistics would favor making the primer chlorine. Just because there's more hydrogens that do that. So it's the bottom one. But we already know because we looked at those bond dissociation energies, these hydrogens are not all identical. So just from the statistics, there's a total of 8 hydrogens you can grab. 2 of them give the 2 chloro, 6 of them give the 1 chloro. If it was just the statistics, we'd expect to see relatively close to that ratio, 75 to 25.
Give me 1 second.
Right, so what we actually see when we do that experiment though is we see 60-40 the other way. So it shows that chlorine is a little bit selective, which hydrogen grabs. It's grabbing the hydrogen and going fast, but there's a little bit of selectivity, because otherwise it would be 25-75 the other direction. So which hydrogen matters, and the stability of the radical matters, but not enough to slow the chlorine down completely. So with chlorine, you get a mess of products. When you do this with chlorine, you get every possible product in somehow. It's going to favor the most substituted carbons, but you're going to get some chlorines put on primary carbons, some chlorines put on secondary carbons, some chlorines put on tertiary carbons if there are any, and then all of those products are sort of mixed together.
It's favored towards most substituted.
Most substituted is going to be favored, but you're going to get some of everything.
Most substituted hydrogens.
Correct. So what this means for chlorination versus bromination is that we were still ending up downhill energy for the intermediates with chlorine, so that our reactants and our transition state were pretty close in energy, made it fast. With bromine, because we're going uphill in energy, that's going to slow things down. And it also means that the carbocation stability is more important. So basically, bromine gets more selective because it's going slower. And it's going slower because these two energies are closer. So our transition state to the bromine looks more like a carbon. Versus our transition for chlorination looks more like a chlorine ring. So in other words, for chlorine, where the hydrogen is doesn't matter as much. For bromine, where the hydrogen is matters a great deal. And so this idea that we can look at how close the transition state is to see what it looks like. Is it closer to the intermediates versus the reactants? It's called the Hammond postulate. And that's not super critical that you know that. But the net result of that Hammond postulate is that if we have methylpropane, we chlorinate it, we get close to the same ratio of both options. If we brominate it, we get almost exclusively the tertiary. So for bromines, we're going to say that we're only going to make one product. If there's one tertiary carbon, that's what we're going to bromine. If all we have, like let's say we were looking at pentane, if you brominate pentane, well, we know that bromination means we're going to put it either carbon 2 or carbon 3, but that does give us two possible products that are relatively close to the same, right? So we're going to have some of this and some of that.
Okay.
What are we going to have more of?
One.
Correct. If there are two options that are equivalent or close to equivalent, that's when you start seeing mixtures. And that's when they're going to be the statistical mixture. By which I mean, for this reaction, there are 4 hydrogens that give us 2 bromo for pentane, right? And there's only 2 hydrogens to give us the 3 bromo. Because what we started with, there was all 4 of those give us 2 bromo pentane versus only 2 hydrogens give us 3 bromo. We would expect to see a 2-to-1 ratio or a 4-to-2 ratio.
Because there's more. ranges.
Because if we're choosing from all of our secondary carbons. And they're all roughly the same, it's gonna be based on probability. So if there's only one option, there's only one product. There's one most stable option, bromine based. So let's try it. It's the same molecule we looked at earlier. If we're gonna brominate it once. What product are we gonna get? Or products if there's more than one option.
Always select. That one.
There's our only tertiary carbon, right? No pi-bonds, there's no resonance to worry about. So if there's a tertiary, that's what we're putting in. If we said fluorination, we're gonna get a little bit of everything. So for chlorination, we're gonna get a product that where we added a chlorine here and here. Because those two are identical. We're gonna get a product where we added it to the tertiary carbon. We're gonna get a product where we added it to the secondary carbon. We're gonna get a product where we added it to each of these metals. We're not gonna have chlorine there though, because it's quaternary carbon, there is no hydrogen flow.
Would you ever have a straw all done with chlorine? Okay.
I certainly might.
Okay.
I won't ask you to predict which one's the major necessarily, because that depends a little bit on the probability. There's one hydrogen that gives you the tertiary, and there's 9 hydrogens that give you that product.
Yeah.
So that's in that gray area. Well, this one's more stable, but there's a lot of options there, so they'll kind of cancel each other out. And you might have almost the same amount of this product versus that product. I don't expect you to know that off the top of your head. What I do expect you to know is that if it's bromine, you get one product. And if it's chlorination, you get a bit of everything. End of slideshow. We made it to the end of the slides today. All right, that's not the whole chapter on free radicals because we're gonna add some more wrinkles next week. But that's your first intro.
I like those.
They're not bad, they're just different than the rules we've had so far. I remember it being, that was the first mechanism that I was taught, and that didn't make any sense.
That was the first mechanism you were taught.
I must be misremembering it because that would be a really silly thing for an instructor to do, but then again, my instructor was very old.
First learners, favorite quotes.
Yeah,
You were supposed to be chapter 1 through 20 over some stuff.
right, basically. I mean, I think the logic was probably start with alkanes, and there's only 2 reactions for alkanes, combustion and free radical.
Right.
So yeah, I was from that point of view, I think. But it really did mess me up for mechanisms for a while because those ones were so different than everything else.
Yeah. I like how you do this. The order's much better.